Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. I was planning actually to start to continue in the session after we were discussing the training in neural networks last time, but I then thought that a hands-on experience, a hands-on exercise on training a neural network specifically will be, I think, useful for you. What we will do today, inshallah, or maybe most of the lecture, we will go through a hands-on exercise together on how we can train a neural network using a backpropagation algorithm. So this is what we saw last time, but we want to have a real exercise. So here's the exercise. I want you to get a piece of paper and try on this, and we will actually have an interactive discussion. So what we want here is to apply backpropagation for 3-class classification with 2-layer network, 2 input features, 2 hidden units with sigmoid. Okay, so we want to apply backpropagation on this network. Right. What is the first thing we should do here? We need to draw the computation graph, right? So to draw the computational graph, we need to know what is the neural network, aslan. Where is the network? Okay, so what is the network here? 2 layers. Okay, so we have one input layer with 2 features. So let's say that this is x1 and that's x2. Then how many hidden layers we have? Just one. How many neurons? How many units? 2 units only. So let's say that this is h1 and that's h2. And then how many output layers? The output layer is just 1, but how many units in that layer? 3. Okay, so 3 units in the output layer. We always have 1 output layer. Okay, so we have 3 units. So this is O1, O2, O3. These are the units. Of course, this is very hypothetical. We usually don't have such setup that the number of output neurons is more than the input features, but this is just for illustration. Okay, of course you can, but that's not that's not common. Okay, and how about the connections? It's feed-forward network. That's the type of networks that we study in this course. So it is between the layers, it is fully connected. Okay, so it is something like this. Okay, so that's the network. Any question about this? So let's also give names to the connections, to the weights. So this is W11. It's going from node 1 here to node 1 here. Let's say that this is also W12. Okay, so W1 and W1 here means the weights for this unit, and this is W21, and this is W22. And similarly here, this is W11. We call it prime, just to distinguish between the weights here and the weights on the first layer. And this is W21 prime, and so on. Okay? And let's also give names to the output. So this is F1, F2, F3. So this is the network. Okay? Right. Now we need to draw the computational graph to do backpropagation, right? So first, before we do any computational graph, we need to know what are we doing, and what computational graph for what. Okay, so what are we doing actually in the computational graph for in this case? Okay, we need to draw the computational graph now, right? For what? It has to be a function. There is a function that we should draw the computational graph for. What do you mean by the sigmoid function? The loss function. Okay, the loss function. Okay, so we are drawing the computational graph for the loss function. Okay, so eventually we have to have the loss value. Type. In addition, we can think of the entire computational graph in two parts actually. Part to compute the output of the network, which are F1, F2, and F3, and then we can extend that. We can use that to compute what? After we compute the output, eventually what should we compute? The loss. Okay, so there are two parts: the output of the network, that's the first part, and then of course the loss depends on the output of the network, right? So we then extend it by the loss part. Okay, so let's focus first on the output of the network. So that means now we want to draw the computational graph for F1 and F2 and F3. Okay, so that's what I want you to do now. You can work together, you can discuss together how we can draw the computational graph for each of these outputs. Where should we start? We should start from the input. Yes. How many inputs we have? 2. And then we move to do the computations, right? Okay. So what should be the computations? It's not only the sigmoid. What are the gates? Exactly. What are the gates? So we need to think about the gates. I will give you a few moments. Think about what we will do. Forget about the loss now. Let's focus on just the output, F1, F2, and F3. Okay, so from the input, we want to compute the output. What are the gates? The gates are what in the computational graph? Are the computations, are the operations, right? So think about how we will convert the input to the output in terms of operations. So if you do that, if you look at the network has neurons, right? Each neuron actually can be seen as a processing unit, can be seen as a gate or one or more gates, right? So if we understand how we map each neuron to gates, then we can replicate it, right? We have 6 neurons here, right? We have 2 in the hidden layer and 3 at the output layer, right? 5. 2 at the hidden layer and 3 at the output layer. If we know each neuron, how we draw the computational graph for, then we can just replicate it for the others, right? So I want you now to start with the inputs and think about how you can draw the part from the computational graph that corresponds to H1, to this node, to this specific neuron, this specific unit, to get its output, which we'll call it H1 actually.
Wait, I'm confused. I always assumed that it was a function, like a mathematical expression.
This is in general. Now that's why I'm doing this exercise now. In general, yes, you will have a function. But for neural networks, you will also have a function, which is the loss function. Okay? So it is inherently or indirectly given here. And we want to draw the graph for it. Okay? But don't worry now about the loss part. Worry about how to draw the graph for the output of the network. And more specifically, for one neuron. So how do you draw the graph, the part of the graph for one neuron only? Yeah, let's say that I want to get H1. H1 is the output of that neuron. Okay? How can I get it? From whatever in the graph. If you know, you can separate them in 2 gates, or you can combine them in 1 gate if you know the derivative for them. Okay? طيب هو if I want to represent H1, what is H1? Yeah, let's assume that we don't have biases, okay? Just for simplicity. Okay, we don't have any biases. Type. What is H1? How can we compute H1? Yes, W11 X1 plus W12 times X2. That's the sigmoid of that, right? So that's the sigmoid. So sigma of this. This is H1. Then knowing this now, how can we draw it? We draw the computation graph for it. We have X1, right? And we have X2. Okay. Then we need to draw this. So X1 will be multiplied by W11. Okay. So let's assume that we can multiply it with W11. So let's say that we okay, we will use a notation here just to make it easier. Okay, so I will write W11 here, and that means that they will be multiplied. Okay, so W11, that's going to a gate. Okay, this gate will do this, which is the weighted sum. Okay, so we'll just call it weighted sum. That's the processing of that is doing this. I mean the process that is doing this computation. Okay, type. What is the input to this gate? X2 also times W12. Okay. Is that H now? Let's call this. This is not H, right? This is, let's say, Z1. Then sigmoid. Very good. Sigmoid. Now this is H1. Okay. Yes. Oh, this is the gate. These are the gates. We can, but the local derivative for the weighted sum is easy also. So instead of simplifying it much more than needed, we just do it this way. Okay, but you can, of course, you can do the multiplication, then the addition. You can, but it is simpler than that. Okay, any other questions? So actually, these two gates is this neuron, right? Type. Then we can do the same for H2, right? So this is W21 and this is W22. That's Z2. Sigmoid. This is now H2. Okay, so this is the part for the first layer. This is for the first layer. Okay. Type. Before we continue, let's make sure that we can compute the local derivatives, because if we are not able to compute the local derivatives, then we'll have to simplify it more. Okay, we have to get maybe into the weighted sum and do it and expand it. So if we look at this gate now, what is the local? How many local derivatives we need to compute? 2, 1, 3, 4, 5. In general, for any gate, when we compute the local derivatives, we compute the local derivatives of the output of that gate with respect to every input of that gate. Okay, so for this gate, how many inputs we have? Not 2. 2 because we draw it that way, but actually it's not 2. It's 4, yes. W11, W12, X1, and X2. Okay, so theoretically we need to compute the local derivatives for all of them, but we are not usually interested in the gradient with respect to the inputs, because we will not change the inputs, right? We need the gradients for the things that we will change. So in this case, we will only compute the local derivative with respect to the weights. Right. Now, what is the local derivative with respect to W11? Of Z1, by the way, okay? We're not talking about H1 now. We're talking about Z1. X1. Very good. Because you see it here, right? So DH1, I mean, this is Z1. This is Z1. Okay? So DZ1 by DW11 is X1. Okay? So let's just give some numbers here to be more specific. Let's say that this is 1 and this is -2, and maybe this is 0.1, 0.2, 0.3, -0.1. Okay, we'll assume that we have current values of the weights. That's what the model that we trained so far, and these are the values. Okay, so now what is the gradient, local gradient with respect to W11? Sorry, what's that? With respect to W11 is 1, because X1 is 1, right? So that would be 1. Right. How about with respect to W12? -2. Okay, -2. Any questions so far? Yes. This is -2. Okay, let me, okay, let me remove this. There was a, okay, so what was the value? Sorry, there was a mistake.
For me, from X1 I have W11, W12. Instead we have W11, W21, so I got confused.
I did it because this is usually the terminology that is used in textbooks, that we start from the destination of the link. And if you think about it, this is because we are talking about the weights going to this node. Okay, so weights going to node number 1 start with 1. Right. So we said that this will be what, -2, right? Okay, any questions so far? Are you following all with me? Are you following with me? Yes? Right. Time. Can we are we able to compute the local derivative for the sigmoid gate? What is the local derivative for the sigmoid? We talked about it last time, right? Okay, so if the input is x, then the derivative is sigma of x times 1 minus sigma of x. Okay, so sigma times 1 minus sigma. So we have to compute the input, right? So can someone compute what will be the value of Z1? Can you do it, please? And then what will be the value of the sigmoid? So Z1 is? I didn't hear you. What is the value of Z1? I think it's 0.1 minus 0.6, right? minus 1. It's 0.1 minus 0.6. Minus? Anyone else? Huh? It's minus 0.5. Type, how about the sigmoid for this? Minus 0.5. 1 over, so the sigmoid of x is 1 over 1 plus e to the power x. It should be close to 0.5. 1 times 0.1 minus 2, minus plus 0.3 times minus 2. Yeah, this, okay, the blue ones are the gradients, the green ones are the values. Ah, okay, okay. Yeah, 0.3 is W12. Let me right. Okay. So what is the sigmoid value? 0.6. I don't think it should be less than 0.5. E power minus x? Okay. Maybe I'm wrong. Not minus x, not plus x. Okay. If x is infinity, then this is 0. Yeah, yes, it is e to the power minus x. So sigma x is 1 over 1 plus e to the power minus x. What will be the value? 0.37. Very good. Okay, type. Now we can compute the local derivative also, right? So what will be the local derivative? Will be minus 0.5? No, 0.37 times 1 minus 0.37, right? Can someone tell me? Right? Are you following? Yes. Of the input, given the input, which is minus 0.5. Z1 is minus 0.5. اتفضلي. في الواقع يا نهار ابيض كلام كبير قوي. يعني ايه في الواقع مش فاهم؟ ما احنا we are starting from scratch. The weights usually we start with random values. We will talk about initialization. I was supposed to talk about it today, but then I thought this exercise I think is important. So we'll talk about inshallah on Sunday. But the short answer is we start usually with random values. Huh? What would be the derivative? 0. 0. I don't hear. 0.23. Okay. Any questions? Okay, we need to be much more faster. طيب, what's the next step? We go to the next layer, right? To the next layer. No, we still we are still in the hidden layer. We didn't get to the output layer yet. Okay, so we need to apply it to the output layer. Where is that? Okay. Okay, so we need to apply to the next layer. So the next layer is just the weighted sum, right? So how can we get from H1 to, how can we get F1? Weighted sum from where بقى? So we have, let's say that this is the weighted sum for F1. What's the input to it? H1 times W11 prime and then from H2 this is W12 prime, right? Do we have sigmoid? No, because that's the output layer. Same for F2 and F3. Type for F2 we get H1 times W 21 prime and from H2 W 22 prime. From F3 we get W 31 prime and W 32 prime. Okay, is that clear? Any questions? Following? Type. Okay, after we compute the so we are done with the output values now, right? Are you following with us? Okay, so what is remaining? The loss. Very good, the loss. Type. How do we compute the loss? Now forget about the entire network. Now we have F1, F2, F3. We need to compute the loss. As we said last time, this is multi-class classification, so we can use softmax to compute the loss. So how can we apply softmax? Do you remember the steps of softmax? So we need to convert these values into probabilities. So what we do is something like this. So this is let's say y1 hat is e to the power f1 over sigma of all the exponentials. J, this is J. So now we want to draw the computational graph part for this. How can we do it? Okay, so we need to raise each value to the power. Okay, so we have e to the power x here. Only one for each one. E to the power x. E to the power x. Okay. Then we divide by the sum. Where is the sum? We don't have the sum. And we said that instead of divide, we need to multiply by the inverse. طيب. Now we need to get the sum. Where is the sum? يعني في الواقع كده احنا بنقعد لكل نتورك we draw the computation graph for it. So what? This will be coded. This will be coded. This will be done automatically. Okay. Why we are doing it? Just to make sure that you understand it. Okay, but all of that will be done automatically. For every gate, we know the local derivative will just connect these together. Okay, and we compute the gradient. will not be able to calculate it on the side. We have to do it now. How can we do it in the graph? For adding them. Yeah, so we'll add them all with one circle, which is the addition. So the addition gate will have all of them. Now this is the sum of them. طيب. Then في حاجة تانية على جنب هنا ولا we converted, we inverted قصدك, we inverted. Now this is 1 over the sum, right? Then multiply بقى ايه? Each one. Because remember, eventually we'll have 3 outputs. Okay? So for the first one, we will multiply what? Huh? We will multiply this one, okay, for F1 with this one. This will give us not the we didn't get to the loss yet, by the way. This is the probabilities. This is the softmax values. Okay, so this one is what do we call it? These are the probabilities, right? y1 hat. Okay, y1 hat. Right. How about the second one? Another multiplication. This one times what? This one, right? Not F2. Not F2. It's the exponential of F2. Okay, which is y2 hat. And then a third one, which is this one with this one, will give us w3 hat. Are we done? No. What is missing now? The loss. Are we ready to compute the loss? Yeah. If the loss is function of what? If you remember the cross entropy, if we're talking here about cross entropy function, the loss function. What is the cross entropy loss function? Minus log. Minus log what? Huh? Minus log which y hat? We have 3. The one for what? Which one? Which one of these? How can we know which one of these? The correct class. So the correct class is also an input to the loss gate. Okay, so we'll add a loss gate here. Call it cross entropy. So the loss gate will have these 3 inputs and also the true label, which is yi. What is I here? I is the number of the index of the example, of the training example. So x1 and x2 here is xi, the vector I, the example number I. So this is minus log yi hat. Type. Now let's see how we compute the gradient for this gate. So can you give me some possible values for y1 hat and y2 hat and y3 hat? What could be possible values? Okay, so each value has to be between 0 and 1, and some of them is 1. So what did you say again? 0.1, 0.3, and this has to be 0.6. Type. Now let's assume that the true label is 2. what would be the loss? Plus what? So this is the loss, right? This is now what we want. What will be the value of the loss? Minus log 0.3. Yes, minus log 0.3. That would be the loss for this example. طيب, how about the local derivative? Now we need now to compute the, this is, we assume طبعا that we computed all the local derivatives up to the last loss gate. Okay, now for the loss gate, what are the local derivatives? Can we compute the local derivatives? What are the local derivatives? Yeah, so it's DLI with respect by D y1 hat and y2 hat and y3 hat. Very good. For this specific example, what would be the values? And first, for the function log, what is the local derivative? Log x. What is the derivative of log x? Derivative of log x? Ln x type, the natural logarithm. We assume here that the base is the natural logarithm. No, sorry? 1 over x, very good. Okay, so it will be, because we have minus here, it will be minus 1 over the input. Okay, type. Now, the local derivative will be minus 1 over each of these inputs? No, because only one of them is used, right? So this one only is used, because the yi was 2. So the local derivative here will be what? Yes, minus 1 over 0.3. This is the local derivative for W2 hat. Just connected. Technology is very bad. طيب, how about y1 hat? 0, because it doesn't depend on y1 hat. خلاص. Okay, so the local derivative for y1 hat is 0. Local derivative for y3 hat is 0 also. Okay, is that clear? Because it's minus log this value only, because the label is 2, so the correct label is 2. So the loss is minus log of this value only, it doesn't depend on the other values. Okay, so the gradient for this will be 0. Type. One more thing before we finish. Any question up to this point? Type. You notice here, back for H1. Okay. For H1, do we need to compute the gradient of F1 with respect to H1? Because H1 is an input also, right, to this gate, right? For this gate, H1 is input, right? So we can compute the gradient of F1 with respect to H1, right? Do we need it? No. Actually, no. Why? Because we have to also compute the derivative of H1 with respect to Z1. Yani, it will be propagated back. X1, because it's at the end, we will not use it. It will change, yes, it will change from by a gradient from F1 and by a gradient from F2 and by a gradient from F3 actually. Okay, so H1 is an input to F1 and F2 and F3. So we need to compute the gradient, the local gradient for it from 3 branches. Remember last time when we had something like this in the last lecture. Okay, when one input branches out multiple branches, so H1 here, and of course H2 the same, H1 here goes to F1 and goes to F2 and goes to F3. So we'll have to compute, for H1 we'll have to compute 3 local derivatives. 3 local derivatives. Okay? Type. When we do the back propagation, we'll have to compute the gradient from 3 paths, gradient of the loss to each one. Yani, let me do it here quickly. So we have here, we have H1 here. Okay, H1 is has branched out 3 ways. Okay, there's path here until L. No, until L even, to the end. And this one also until L. And this one till L. Okay, from all of these branches. So we will compute local gradient on this from this path. Okay, so that's the, I mean, not the local gradient, the actual gradient up to here, from the output up to here, on this path, and on this path, and on this path. Now, what is the actual gradient of H1? The sum of them. Okay, is that clear? Exactly, yes. Last lecture, yes. Okay, طيب, how will we compute this one? This is by chain rule. We propagate back from L up to this variable. Okay, same here, and then we add the gradient. Now, let's say that there is a gate here, and there is another variable here. Let's say that this is Z1. Okay, now when I propagate the gradient back, which one I will use for H1? This or this or this? لا, يعني كلهم. I will use one of them. I will have to use one value. Which value? The sum of them. Yes, that's the answer. مش كلهم. Okay, the sum of them. Okay, so the sum of them will be propagated back. Okay, is that clear? Yes. Of course, this is also same for H2, same for this output. Although we didn't give it a name. Okay, but any branching means that there is derivative from each of these paths, from the final output through multiple paths. So you have to add up the gradients at all of these branches, and that will be the total gradient for this variable. طيب, this is not a parameter of the network. يعني مثلا H1 is not a parameter of the network. Why are we interested in computing the gradient of the loss with respect to that variable, although it's not a parameter of the network? Because it will be used back. يعني we will use H1 to, the gradient of H1 to compute the gradient of Z1, to compute the gradient of W11, and so on. Okay, so we'll have to do the back propagation of the gradients. Eventually, we are only interested when we do the update bar. When we get back to the inputs, now we have the gradient for everything, for all the variables, including the parameters and non-parameters. Now we can do the updates. Okay, only for the parameters of the network, which are the weights and biases, if we have biases. Is that clear? Yes. You have a question? أنا مش فاكر إيه السؤال عن الإف1. F1, yes. Which derivative? يعني طبعا, yes, of course, because we'll need the derivative of F1 to multiply it by the local derivative. Okay, يعني we'll need all, يعني we'll have to compute all the local derivatives except the derivative of the very first inputs. The local derivatives, F1 with respect to W11 prime and W21 prime, and H1 and H2. Yes. Is that your question? Is that clear? Was it useful? Okay. Now I think you understand better how things are going in training. This is of course for one example. Okay, and we started, as you see here, we put values for one example, right? We computed the loss, we computed back the gradients, we update the weights. Of course, if we are doing stochastic gradient descent, as we will inshallah discuss next lecture, or we accumulate the weights, the gradients, okay, to update the weights, and then we'll get new examples and so on. Any questions? Okay, thank you.